And the recording will get posted right here in the class recordings section. So the first couple numbers are the day that we had our class on and the day that it was recorded, and then the name of whatever kind of subjects that we talked about on that day. So we are in week 2 now, which means we are starting to talk about properties of matter. Matter is just sort of a fun science word for everything around us in the universe. Everything is considered matter. And so today we're going to talk about kind of some basic things that you maybe hadn't really thought of before as being particularly sciencey, but do play an important role in scientists and how they design experiments and stuff like that. So we're going to be actually covering 2 topics today. One of them, they both kind of tie into each other. The first one has to do with matter and phase changes. So how does matter change between one state of being and another one? And then the second kind of little short mini section of notes for today will be about heating curves, which are graphs that show the temperature of a specific piece of matter as it gets heated up over time. And we'll talk about what are some of the things that a heating curve can tell us about that particular state of matter. So while I'm going ahead and getting these notes loaded up, does anybody have any questions about anything from the first week of class or anything kind of from Monday of this week? Anybody have any questions about anything or anything that you want me to go back and address really quick before we get started here?
I wasn't here for the first class. Did I miss anything like super interesting?
Not really. We basically just kind of talked about the class a little bit, and I talked about the attendance policy, which is basically just making sure that you're checking in every day, either doing your daily assignment, coming to class, or communicating with me some way so that you don't fall too behind.
All right, cool. Word.
All right. So the first thing that we're going to talk about today has a little bit of some new stuff and a little bit of some stuff that you've probably heard about and know about before, but maybe haven't thought about it in specifically a scientific term. So like I said, matter is kind of the general science term for just stuff in the universe, right? Whether it's gas out in space, or a solid buried deep under the earth, or a liquid floating around in the ocean, everything in the universe is made up of matter. And one of the cool things that scientists discovered about matter is that matter is made up of even smaller, constantly moving particles. So these particles are called atoms. And if you've heard about atoms before, that's great. We're actually going to talk a lot about atoms in a couple weeks in this class. But these tiny atoms that make up everything else in the universe are what make up the matter. And so one of the things that scientists found about the atoms that make up the matter in the universe is that they are actually constantly moving. So whether they're moving around really, really fast, or they're barely moving, or they're just kind of vibrating in place, they're doing some sort of movement. And so the kinetic molecular theory is a big scientific way of saying the theory about how tiny particles like molecules move. So kinetic in science relates to like movement and motion. So kinetic molecular theory just means tiny moving particles. And these particles are what go into making up everything else in the entire universe. So something else that scientists found out about these little particles is that as you increase the temperature of your matter, the kinetic energy or the movement of these particles goes up. It increases. So the hotter that you get, the faster that the particles are moving. So you could take these particles from being relatively still, just kind of vibrating in place. And if you heat them up enough, you can get them to start zooming and flying all around the room. So why are we talking about this kind of complicated thing about these tiny particles that are moving and they move faster when they get hotter? This actually is what makes up the kind of backbone for the three different states of matter that we're going to talk about. So while you may not have heard them referred to as the three states of matter, what you have probably heard before are solids, liquids, and gases. So that's what we mean by three states of matter: solid, liquid, gas. There is actually a fourth state of matter. It's called plasma, and it's kind of very complicated, and it really only happens out in space, and so we're not really going to talk about it in here. So the three main ones are solids, liquids, and gases. And so for each of these states of matter, we're going to talk about some of the properties of that state of matter, specifically how much energy do the little particles have inside of it, what kind of shape does it have when it's in that state, and what is its volume, how much space does it take up. So we start off with solids. Solids have the lowest amount of Ke, which stands for kinetic energy. So before, I was talking about kinetic means like movement and motion. Solids have the least amount of motion. Think about it. If you look at the computer in front of you or the desk that your computer's sitting on, it's not really moving a whole lot. It's staying pretty steady. So the particles in a solid have very low energy. They can kind of like vibrate around each other a little bit, but they're not really moving all around willy-nilly. They're staying pretty much put. Solids also have what's called a definite shape and a definite volume. And what I mean by that is that it's defined. So a solid will always be the same shape, right? If you take like a metal block, like this guy right here, we have this little block of particles right here. If you took it out of this vase and put it on a table or held it in your hands, it would still be shaped like a block, right? My computer mouse is going to stay in this particular shape of being a computer mouse, no matter where I put it. If it's on my computer, if it's on my table, if I throw it on the ground, it's still going to be computer mouse shaped because it is made up of plastic that is a solid. Volume is how much space that an object takes up, and solids have the same shape always, so they also will always take up the same volume. No matter where you put that solid, it is going to have the same shape and take up the same amount of space. This little block will always be 3 particles by 3 particles, and it will always be shaped in this square block formation right here. That is the characteristics of a solid. Low energy, the shape is set in place, it doesn't change, and the volume is also set. It's not going to just randomly get bigger or smaller. It's going to stay the same volume. So, particles, low energy, very close, very stuck together. But what about if we increase the energy a little bit and make it so that now those particles can kind of move around? They can rotate, they can spin, they can move around each other. Well, then you just converted your solid into a liquid. So liquids, as you might imagine, have a little bit more motion than solids. They have a little bit more energy than solids. So liquids have a higher energy compared to their solid counterparts. The particles are a lot more movable. So the particles are moving all around one another. They're still kind of staying close together. They're not completely zooming off and flying all over the place. So they're still kind of stuck together a little bit, but there's a lot more motion. There's a lot more movement that can happen in a liquid versus in a solid. One of the big things that results from this is that liquids have what's called an indefinite shape. A liquid does not have a defined shape. Like if I try to ask you, hey, what shape is water? That question doesn't really make sense. Water can be whatever shape that you want it to be. So the shape of the liquid changes to fit whatever container that it's in. If I take some water out of the pipe and put it into my cup, now it's just gone from being in a tight little hole in the pipe to filling up the bottom of my cup. If I take my cup and spill it all out on the ground, now the water has spread out and is making a really thin layer across the tile in the classroom. So the shape of the water, the shape of this liquid is changing. It depends on where you put it. If I took my circular cup and emptied the water out into like a square Tupperware, the water would form the shape of a square because it's just filling up the Tupperware that you put it in. So that's what we mean when we say indefinite shape for liquids. They don't have a set defined shape. They kind of take up whatever shape of the container that you put them in. Liquids do, though, have a definite volume. So they don't have a definite set shape, but they do have a definite volume. Meaning that if I take a cup of water and I put it like one fluid cup of water, and then I pour it into my water cup, and then I pour my cup into a pan, that pan is still going to have 1 cup of water. The volume of the water didn't go up or down, even though I changed what shape it was and where I put it. The volume was set. A cup of water is a cup of water no matter what kind of container that you put it in. It's just the shape of the liquid that changes. So liquids, higher energy, right? Liquids are a lot more motion than solids. You get a lot more moving around of liquids. If you jiggled this test tube a little bit, the liquid in here would be jostling all around here on the bottom. Don't have a set shape for liquids. They take up whatever shape of the container that you put them in, whether it's like a tube or a beaker or a cup or a pot, whatever it might be, they're just going to take that shape. But it's still going to be the same volume. It's going to take up the same amount of total space, whether or not it's in a big container, a medium-sized container, a small container, whatever size it's in, it'll keep the same volume. A cup of water is a cup of water no matter where you pour it out into. So we have this water or whatever liquid that you want to deal with. The particles are kind of moving around. They're sticking close together. So we have sort of this medium level of kinetic energy. But what if we really wanted those particles to go? What if we cranked up the temperature and got our liquid hot enough so that the particles started flying away from each other, having a lot of movement and zooming all over the room? That state of matter we would call a gas. So we add in some more heat, and now we have changed our liquid into a gas. So gases have the highest of the energies, the kinetic energies that we're going to be talking about in this class. So the particles don't have to stay close to each other like they do in liquids and solids. Instead, they can separate and move throughout the container or the room or the environment that you put them in. So gases are tiny, they tend to be invisible, and the particles are extremely fast moving. The cool thing about gases is that they do not have a definite shape and they do not have a definite volume. So if you take some gas and put it into a container like a oxygen tank that a diver uses when they're going scuba diving, there's a lot of gas in the tank on their back. The gas doesn't just all sink to the bottom and sit down on the very bottom, right? It expands, it fills up the container that it was put into. The volume of it increases. So the shape and the volume of gases are totally dependent on what kind of container they are inside of. Gases have enough movement where the particles can completely separate from each other and totally fill up the space that they are put into. So a lot more freedom in gases versus liquids and solids. A lot more energy, a lot more movement, a lot more changing of shape and volume.
You sipping on water?
Yeah, exactly. I got some liquid water in here with some solid. You can't really see it because I don't want to spill on my computer. But there's also some solid water floating around in it.
Ice.
Whoops. Yeah, there you go.
Word.
All right. So we've got our solid that has the lowest energy, particles very close and stuck together. And it has a set shape and a set size. It's not going to change no matter where you put it. If we bump up the energy level a little bit, we can get liquids, have a little bit more energy, a little bit more motion of the particles than the solids. They do not have a set shape. They kind of fill up whatever container they go into, but they do have a set volume. They're going to stay the same volume no matter where you put them. Finally, if you bump up the energy level even more from the liquids, you get a gas. So the highest amount of energy are in gas particles. They do not have a set shape or a set volume. They can change shape, expand, contract, get bigger, get smaller in order to fill up wherever you put them in. So that is sort of the scientific way of thinking about solids, liquids, and gases, things that you probably interacted with on a daily basis for most of your life without even really thinking about it. So does anybody have any questions about solids, liquids, and gases so far? Anything that you want me to go back and review a little bit? Does not sound like it. So now that we know a little bit about specifically the different states that we're dealing with in this class, the next thing to kind of logically talk about is how do we get from one state to another? And specifically, what is it called when we change from a particular state to a different one? So we call these changes phase changes. We're changing from one state or one phase to another, either going from a solid to a liquid, or a liquid to a gas, or a liquid to a solid, whatever it might be. Going from one of these states to another one, either by warming up or cooling down, is called a phase change. And we have specific words to describe when we're going from one state to another. So the first couple ones here, I'll have you guys help me out with because you've probably heard these used a lot before. So if I describe something as melting, what are the states that it is changing between? We're going from what state to what other one?
Solid to the gas. No, solid to the liquid. My bad.
Mm-hmm. Yep, exactly. Yeah. Melting is solid to liquid.
Going too fast for myself. God damn.
That is solid. We heat it up a little bit. It starts to change into a liquid, and we call this change melting. So if you leave some ice out on your counter, or you have something that is like a hardened ice block in your freezer, and you got to start thawing it out, the ice in there is going to start melting. So this also happens a lot with like industrial stuff that has to melt a lot of metals in order to make new forms and new shapes. Obviously, that happens at a much, much, much higher temperature than going from ice to water. So anytime anything is going from a solid to a liquid, no matter what temperature it's at, we call it melting. What about if we go the other way? What if we take something liquid and cool it down to the point where it becomes solid? What do we call that process?
Wait, what?
So we have something that is liquid, and we cool it down until it starts forming a solid.
So from solid to liquid, liquid to solid?
Sorry, yeah, liquid to solid. What is that phase change called?
Solidifying?
Close. There's a little bit more specific name for it, though.
Anybody else want to take a stab at it?
If you want to make ice cubes, you fill up your little tray with water, and then where do you stick that tray?
Freezer.
The freezer, exactly. And so it's called freezing.
Wow, okay.
So I know, I'm telling you guys, it's a lot simpler than you might think. So freezing is when we go from a liquid back to a solid. We take something that is liquid and then cool it down, remove some of that energy. The particles start moving slower and slower and slower until eventually they stick together. And that's what forms a solid. So in the case of water, we have to cool it down to below 32 degrees Fahrenheit. And then that water will start changing into ice. And we call that freezing. So melting, going from solid to liquid. Freezing is the other way, going from liquid to solid. So the temperature that this happens at, it can be called either the melting point or the freezing point. Because say for water has a melting point / freezing point of 0 degrees Celsius, which is about 32 degrees Fahrenheit. So if you take some ice and put it somewhere that is above 0 degrees Celsius, it'll start to melt. If you take some water and stick it somewhere that is below 0 degrees Celsius, it'll start to freeze. And so whatever that temperature point is, that is where this specific temperature is where this phase change happens. Whether or not we're going from solid to liquid or liquid to solid, it kind of revolves around a specific temperature, which is unique for any type of matter. So every different type of matter has a melting point / freezing point. Water is just probably one of the most common ones that people deal with on a regular basis. So it makes for a really, really nice example. All right. So up next, we have some other changes that you've probably seen happen in front of you without really thinking about it. The first one is changing from a liquid to a gas at a temperature called the boiling point, which is called vaporization. So vaporization is the term for when you heat something up that is a liquid until it starts boiling. So vaporization is basically sort of like the fancy science word for boiling. So at some point, that liquid is going to be getting enough heat to where it'll start changing into a gas. So when it's happening at that boiling point, we call it vaporization. So you're getting ready to make some pasta. You put some water in a bowl. you crank the stove on super high, and after 5 or 6 minutes, you start to see all those little bubbles start to appear, and all that gas starts coming off the top of your pan. Those bubbles are just little bubbles of water vapor that are coming up out of the water and forming the gas water vapor above your pot on the stove. So that's called vaporization, when we heat that liquid up really high and it starts boiling. There's a second way that we can go from liquid to gas. It's called evaporation. So this is what happens when we have a much kind of slower, long-term change from liquid to gas. So think about like after a big rainstorm or something, then the next day or maybe later in the afternoon, you go outside and you can see along the sidewalk or maybe in the street, there are these big puddles of water, right? That are just kind of sitting there. And then by that same time the next day, those puddles are mostly gone. The water has evaporated. Now the water did not turn to gas because it got to the boiling point outside, because that'd be very, very bad. The boiling point for water is about 212 degrees Fahrenheit. So hopefully it's never 212 degrees outside, because that'd be bad news for everybody. But slowly over time, liquid will generally kind of spontaneously change and become gas. It doesn't happen super fast, quick like in vaporization, but it still happens. It's another way to go from liquid to gas. So evaporation is also a type of phase change. If we want to go the other way, take a gas and cool it down to where it starts becoming a liquid, that is called condensation. So condensation is when you have a gas that you cool down enough to where the little gas particles start kind of clumping up together and forming little water droplets. So condensation is the reason why we get rain. There's a whole bunch of water, that's water vapor, that's a gas, floating around in the atmosphere above us. Eventually, it'll cool down to the point where it starts to kind of clump together a little bit and form initially clouds at first. And then eventually it'll cool down enough and there'll be enough water around to where the water vapor starts to clump together and form little water droplets that then fall down to the ground as rain. So all that happened was we cooled down water vapor gas to the point where it started forming liquid water droplets, which then became too heavy to float around in the air, so they fell down onto the ground as rain. So we took our solid, we can melt our solid to turn it to a liquid, we can vaporize or evaporate our liquid and turn it into a gas. We can also condense our gas to turn it down into a liquid, and then we can freeze that liquid in order to turn it into a solid. So these are things that you've probably seen and experienced at some point over the course of your life, maybe without really seeing it or realizing it, but that is what was happening. There are a couple different ways that we can go through phase changes, however. That are a little less common, but very, very cool, in my opinion. So we've gone solid to liquid, liquid to gas, gas to liquid, liquid to solid. But we haven't talked about going directly from solid to gas or gas to solid yet. That is a phase change that can happen in the natural world. And when we go directly from a solid to a gas, we call it sublimation. So sublimation is what happens if you have a very, 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 very cold solid and you put it somewhere that is very, very warm or very hot. So a good example is dry ice. which people like to use at parties and stuff to keep drinks cold, but also a lot of special effects people use it because it creates this really cool kind of mist fog sensation coming off of it. Dry ice is blocks of frozen carbon dioxide gas. And when you put that frozen carbon dioxide, which is at negative, I want to say it's like negative 80 or 90 degrees Celsius, when you put it into a 70, 80 degree room for a party, that is a huge temperature difference. So the solid gets so hot that it starts to change not into a liquid, but it skips that step entirely and goes straight to a gas. So we call that sublimation. When you heat up a solid so quickly that it turns straight to gas. You can also have this happen in the other direction, where we call it deposition, where you cool down a gas extremely quickly and it skips the liquid step entirely and goes directly to being a solid. So these two guys are a little less common. You don't see them as often in kind of your everyday life, but they do happen, and it's essentially due to big temperature changes, either heating up a solid extremely quickly or freezing a gas, or I should say cooling down a gas extremely quickly. Either of these will create this direct solid to gas or gas to solid phase change of either sublimation or deposition. So if you've ever seen like dry ice somewhere and it's this solid block and it almost looks like it's smoking, like there's smoke coming off of it, that's not smoke, it's just gas form of the solid that's kind of steaming off from being so relatively hot. So if we put everything together into kind of one image, we get this handy dandy little picture down here where we have our three states of matter, our low energy solids, our medium energy liquids, and our high energy gases. So if we take a solid and want to turn it into a liquid, it'll go through melting. And then if we heat up a liquid and change it into a gas, we call it either boiling or vaporizing or evaporating, whatever kind of best works for the situation. If we cool down that gas and turn it into a liquid, it goes through condensation. And then if we cool down that liquid even further and turn it into a solid, it goes through freezing. And then finally, if we heat up that solid extremely quickly and it starts to directly turn into a gas, we call that sublimation. And then finally, if we cool down that gas really, really quickly and turn it directly into a solid, it goes through deposition. So solid, liquids, and gases are all connected, and it all has to do with how much heat or how much energy goes into them. All right. Any questions about the phase changes, their names, or what they mean? Any sort of questions about this stuff so far?
No questions.
Agreed.
No? Like I said, a lot of this stuff is probably stuff that you have, in a way, seen or heard about or thought about at some point in your life before, just maybe not kind of exactly in this way. All right. So we do have kind of one more set of notes to talk about regarding these changes between solids, liquids, and gases. But before we do that, I wanted to kind of briefly show off the homework for today, the daily assignment for today. Pretty short and straightforward. It's a couple different parts. The first part is just, it has a little bit of information about the different states of matter that we just talked about. It then has these 3 images of particles, and it's up to you to tell me if this diagram is either a gas, a liquid, or a solid. So we have the left diagram, the middle diagram, or the right diagram. We also have a little kind of review of what the different phase changes mean and what the names for them are. And then we have this final kind of triangle image, very similar to the one that we just looked at on the notes, where each one of these arrows has a little label on it. So this guy right here is arrow 1, and then this guy over here is arrow 2, arrow 3, arrow 4, arrow 5, and arrow 6. And then I just want you to tell me which phase change do each one of these arrows represent between freezing, melting, vaporizing, condensation, sublimation, and deposition. Which phase change goes with which arrow? So 6 arrows, 6 phase changes. So that is what your Tuesday assignment looks like. And then your Wednesday assignment, which we'll talk about in a couple minutes, is related to this next short set of notes that has to do with a type of graph called a heating curve. So I would definitely recommend that you pay close attention to the next couple slides, because every term, this is kind of the first thing that really trips people up in IPC, is figuring out what's going on with these heating curves. So these heating curves are, like I said, a type of graph, and I'll show you what one looks like in just a second here. They're also sometimes called phase change curves or phase change diagrams. And it essentially shows you the temperature of a certain piece of matter as heat or energy are added over time. So it's basically, think about like somebody stuck a thermometer inside of a piece of matter and then put that piece of matter onto like a stove or a hot plate somewhere and are watching the temperature as time goes on. So as you might imagine, the longer that it goes for, the higher the temperature will get. But the temperature doesn't just steadily increase from one point to another. Instead, it creates this series of curves that we're going to talk about. So if you remember earlier, we were talking about kinetic energy and the kinetic molecular theory, and that idea of we have these tiny particles and they're either in solids, not really moving, and liquids have a good amount of motion, and then in gases are moving super quickly and super fast all around. And we talked about how as the temperature goes up, the movement of our particles goes up. And so when our particles are faster, in science we say that they have higher kinetic energy. So higher kinetic energy means that the particles are moving faster and faster, which is generally due to the temperature of our matter getting hotter and hotter. So here we have our heating curve. You'll notice that it is not just a straight line from our point down here to our point up here, right? Instead, we have these parts where the line is going up and these parts where the line is flat. So over here on the left-hand side of the diagram, on the y-axis, the vertical axis here, displays the temperature that our matter is at. And then on our x-axis down here is just the amount of time that our matter has been heating up for. So in this specific case, the example heating curve that we're looking at is the heating curve for water. So if you imagine somebody stuck a thermometer and a big ice block and then put that ice block on a stove, this is what the temperature readout of that thermometer would be over time. And so the two kind of major areas of the heating curve that we're going to talk about today are the areas where the temperature is going up and the areas where the temperature is not going up, where it is staying the same or where it is flat. So when the temperature is going up, that means that we have some sort of matter that's staying in one state, one phase, and the temperature of that matter is just increasing. So like I said, we're starting off with a big ice block. This is a very cold ice block. It's at about -20 degrees Celsius. And so this first little part here where it's going up, the ice block is heating up. So it is possible for ice to start getting warmer without yet melting if we're staying underneath that melting point. So down here, the first part of the heating curve, we have the ice that's warming up. The Ke here, remember, has to do with the kinetic energy. So as the temperature gets warmer, the ice particles start to move a little bit faster and faster. Same thing with the middle section of our heating curve here. Now we have liquid, in this case, liquid water, that again starts off at a pretty low temperature and then is getting hotter and hotter and hotter. So that's what's going on in this middle section right here, is the liquid water is heating up. So this would be like once all the ice is totally melted, and now you have that water on the stove, and that pot of water is going to get hotter and hotter and hotter over time. That's exactly what's happening in here. Finally, eventually, if you put enough heat into that water over time, you'll turn that water into gas. And so the last little bit of our heating curve here, this kind of final little leg of increasing temperature, just refers to now all of the gas is being heated up by this heat source as well. So when we have these areas of the heating curve where the temperature is going up, it just means that we have a particular state of matter, either a solid, a liquid, or a gas, that is increasing in temperature over time. So either the ice is getting hotter, or the water is getting hotter, or the water vapor is getting hotter. That's what's happening in these sections. So the reason why it's saying Ke up, it just means that the particles of this state of matter are starting to move faster and faster over time. Their kinetic energy is going up because the temperature is going up.
All right.
All right, everybody feel okay with sort of this first part of the heating curve so far? Any questions about these three sections, the solid, liquid, or gas sections?
No questions.
All right. So if everybody feels kind of okay with those sections, the next sections that we're going to talk about are these big flat sections right here. So before we can get directly to those flat sections, we have to talk about something called potential energy. So before we were talking about kinetic energy, this Ke, where it's talking about the energy of particles moving around and moving faster or slower. Potential energy is similar, but instead of looking at how fast the particles are moving, instead potential energy looks at how close are the particles to each other. How tightly are these particles stuck together? If something is low potential energy, that means that its particles are very close together, like a solid. Versus if something has a really high potential energy, that means that the particles are spreading far apart, getting wide apart, like in a gas. So where the potential energy comes into play has to do with these phase changes. So before, we talked about the solid is heating up, the liquid is heating up, or the gas is heating up. Now we're going to look at the solid is changing into a liquid. The liquid is changing into a gas. So as we go through these phase changes, our potential energy increases, because when we go from a solid to a liquid, the particles spread out a little bit. And then when we go from a liquid to a gas, the particles spread out even more. So as the particles spread out, potential energy goes up. So the reason why we have those flat parts on the graph, that I'll go back and look to in just a second, is that while we are changing phase, while we're changing that potential energy, the particles themselves are not getting any faster or slower. They're just kind of being moved apart from one another. Since they're not getting any faster, the kinetic energy stays the same, which means that the temperature also stays the same. So that's why on our heating curve, in between the solids, the liquids, and the gas, we have those flat sections. The temperature stays the same because the matter is not getting any hotter. Instead, it is changing phase. So if we go back to our heating curve, we start off with that really cold block of ice. It gets warmer and warmer until it hits that melting point, which in the case of water melts at 0 degrees Celsius. So once that ice block hits 0 degrees, it starts to melt. And while it is melting, even though it is sitting on a stove that has the heat turned on, that icy water isn't getting any hotter. Instead, we're taking all of that solid and turning it into liquid. We are melting. So our potential energy is going up because the particles are getting spaced apart. They're going from tight solid to spaced out liquid. But the temperature is not going up. It's staying the same. So this first section down here is for melting. We're going from a solid to start off with, and we end up as a liquid at the end. Remember, melting, solid, going to liquid. And then the second section up here is boiling or vaporizing. So now we have that liquid. It's starting to heat up. It's getting hotter and hotter until it hits the boiling point for the liquid. In the case of water, the boiling point is 100 degrees Celsius. So once that water hits 100 degrees Celsius, it will not get any hotter than that while it is boiling and turning into a gas. So boiling or vaporizing, however you want to phrase it, the temperature of the water stays the same because it's going through that phase change. It's being vaporized from a liquid into a gas. The particles are getting even more spread out and spaced apart, but they're not actually getting any faster during this process. So the temperature is not going up. So if you start your water for pasta and it hits that boiling point and you stick a thermometer in it, it's going to read 100 degrees Celsius. and it's going to read either exactly or pretty close to 100 degrees Celsius the entire time that the water is boiling. So boiling water cannot get much hotter than 100 degrees Celsius. It's taking all that energy, and instead of getting hotter, it's converting it to make water vapor, that gas that is going to come off the top of your pot. So only once all of the water vapor boils away and becomes, or once all the liquid water, vaporizes and boils away and becomes gas, then we'll start to increase the temperature of the gas after that. But while the water is boiling, the temperature of the water is staying the same. So again, these flat sections down here, the temperature is staying the same because our matter is going through a phase change. Either we're melting from solid to liquid, or we're vaporizing or boiling from liquid to gas. All right, so one kind of final look, if we put everything together. So we have our big block of ice. We stick a thermometer in the top and stick it on the stove. Initially, that ice will start to get warmer as the ice block heats up. Eventually, that solid ice will hit 0 degrees. When it does so, that solid will start to melt. While the solid is melting into a liquid, the temperature of the solid stays the same. It does not change while this melting is going on. Eventually, we'll take all of the solid and melt it all into liquid. Then the temperature of that liquid, in this case liquid water, will start going up. The liquid is getting hotter and hotter. The particles of the liquid are moving faster and faster until eventually that liquid reaches its boiling point, which for water is 100 degrees Celsius. The liquid starts to boil. All those bubbles are being vaporized and turned into a gas. But again, the temperature of the water stays the same. While this boiling and vaporizing is going on, the temperature does not go up. All of that energy instead is going into breaking apart the liquid molecules into gas molecules, which can go and zoom around the room. It's not until all of the liquid eventually gets all vaporized and boiled away that we then start getting the energy, the temperature of that gas to start going up again. So we start off with our solid. It then goes through the melting phase change and becomes a liquid. That liquid starts to heat up until eventually it starts going through the vaporizing or boiling phase change to become a gas, at which point that gas will start to heat up at the end. So this is kind of what's going on as we're looking at our heating curve. It's telling us where are the phase changes between the solid and liquid or liquid and gas parts happening. And we can tell that a phase change is happening because the temperature will be flat during that time. It'll stay the same for several minutes. It will not go up, even though it's sitting on some sort of heat source. That phase change is taking energy away from making the particles hotter and putting them towards changing into a liquid or into a gas. All right. Anybody have any heating curve questions right now? Anything that you want me to go back and talk about with this heating curve right here?
I'm good.
Yeah, I think you just about said it all, man.
Awesome. Thank you, guys.
No.
All right, great. Thanks, Dwee. So the reason why I like to go into it kind of like over and over again in such great detail is that it always trips people up and they see it and they think they get it. And then later on, they're like, wait, I don't remember what that one part meant. So remember, I am recording this, so you're always more than welcome to go back and watch the recording and going through this step by step if you think that'll be helpful. Or just reach out to me directly, send me a text or an email, and I'll either kind of text or email you back and help you figure through it. Or if you want to, we can set up some time to kind of work on it one-on-one if you're still confused. So the reason why I bring that up is because Wednesday's assignment is specifically about heating curves. So it's set up a little bit differently than the heating curve we were just looking at, but it has the same basic parts. And again, it says we're attaching a thermometer to an ice cube. So we're dealing with water here. And so we're starting at a very cold period down here. And then temperature goes up, and then the temperature stays the same for a little bit. And then the temperature goes up again, and then it stays the same again, and then it goes up again. So same basic format as the heating curve we were just looking at in the notes. And then there's a series of questions essentially asking for between A and B or B and C or C and D, what's happening. And so I think the first one is saying that what's going on between A and B. And then it's asking, okay, the temperature, there's something going on there between B and C. What is it doing? As for the temperature, if you're able to measure the temperature of the icy water between B and C, and then between C and D, D and E and F, essentially either what state of matter are we in, what's going on with the temperature, or why is it going up or down? So some basic questions that, as long as you kind of remember what's happening in these basic parts right here, you should be pretty well equipped to answer. All right, anybody have any questions on the heating curve homework here? All right, so again, this will be posted on Wednesday. So this will be like your Wednesday daily assignment to work on in order for that attendance credit. And then on Thursday, we're going to come back together and talk about some chemical and physical changes and properties. So what are some of the different things that we can observe or measure about different types of matter? All right, so let me go ahead and get out of that stuff. So that will just about do it for the kind of stuff that we're going to cover today. Does anybody have any final questions about the states of matter, the heating curve, or the homework assignments before we wrap things up for this afternoon?
I have a question. For today's assignment, it has the template and it has another. Do we do both of those?
So they're both the same thing, actually.
Uh-huh.
So it just depends on which version that you'd rather do.
Oh, okay. So we just choose one.
I know some people like the Google Form version. Some people like the Google Docs version. I think the one that I was showing you guys was the Google Form version. So that, oh wait, hold on, that's the wrong thing. So that's the one that looks like, hold on, let me bring it back up here. Okay, Tuesday assignment. So the Google Form version is the one that I was showing you guys a little bit earlier, where it has the different questions and then the arrows that you label on the bottom. The Google Doc version is the exact same questions, just in a little bit different version. Because I know some people like going in and working on the doc more than they like the Google Forms. And so this one, basically the same thing. You write in the gas, liquid, or solid label for these diagrams and the little blanks down here. And then it has the same diagram with the labeled arrows, and you just put in the names of each arrow on the numbers over here. So a lot of the assignments that you'll see me post on here will have a Google form or a Google Doc version. You are free to pick whichever one works best for you. But they should, in pretty much all cases, they'll be the exact same homework, just in different forms for you to pick from.
Okay, thank you.
No problem. Thanks for having me point that out. All right. Any other final questions before we sign off?